Today we will talk about why IPv4 broke and why V6 exists. Because the internet was never designed for this many devices. IPv4 reached its limits. Today we'll talk about why V6 had to replace it. The internet was built in an era when nobody expected billions of devices to connect to it. Engineers designed a protocol called IPv4, which worked well for decades. But its design assumed a far smaller network than we have today. Today, every phone, server, laptop, sensor, endpoint, camera, encoder requires an IP address. That assumption collapsed. The result was a structural limitation that forced the development of IPv6. IPv4 was built with a fixed address space. The main idea is that it uses a 32-bit address system. This design allows roughly 4 billion unique addresses. Every V4 address contains 4 octets written in dotted decimal formats. An example is like 192.168.1.1. Each octet represents 8 bits. 4 octets produce 32 bits. Now, if we compare that to V6, this structure sets a hard mathematical limit on how many unique addresses can exist. As the internet expanded globally, the limit became a serious constraint. Large organizations originally received entire address classes. Class A, for example, ranged from 0 to 126.x.x.x. Class B and C ranges served medium and small-sized organizations. These allocations consumed the address space quickly. The world ran out of public V4 addresses. IPv4 could not support the scale of the modern internet. As networks expanded, billions of devices needed addresses. The original V4 pool contained fewer than 5 billion addresses. That number might appear large at first, but becomes insufficient when every endpoint and IoT device requires connectivity. Engineers introduced workarounds to slow the exhaustion of V4 addresses. There are two major techniques that appeared. The classless interdomain routing, we can short that as CIDR, and the network address translation, you can short that as NAT. CIDR improved address allocation efficiency. NAT allowed many private addresses to share a single IP address. These methods delayed the exhaustion but didn't fundamentally solve the underlying limitation. Private address blocks were created to support NAT, like the 10.00/8, 172.16/12, and 192.168/16. Devices using these addresses cannot communicate directly on the public internet without translation. IPv6 was designed to remove the limitation. IPv6 expands the address space dramatically. It uses a 128-bit address structure instead of 32 bits. This change increases the address space to an extremely large number of unique addresses. Addresses are written in hexadecimal format as opposed to dotted decimal and separated by colons like 2001, DB8, ABCD, and you see the rest on screen. This structure supports hierarchical addressing and allows networks to allocate enormous amounts of subnets. Organizations often receive a /48 allocation, which alone contains a 65,000 and change of subnets. A company assigned 2001 DB80 ABC/48 can create subnet ranges such as 2001 DB80 ABC01/64 and 02/64. This structure scales far beyond IPv4 addressing. IPv6 also redesigns the protocol. The idea was that V6 was not only designed to increase the address capacity, it also simplified packet processing. IPv6 introduced several structural improvements. Some of those are the fixed header length of 40 bytes, the removal of the header checksums. This is left for the upper layer protocols, the simplified extension header model, and the improved packet processing efficiency. In contrast, IPv4 headers vary in size and require additional processing overhead. This makes it less efficient than V6. So these changes allow routers to process packets more efficiently. That's why V6 is said to be more efficient than V4. In V4, for example, routers may fragment packets when necessary. In V6, only the sending host can perform fragmentation. Routers no longer perform this operation. This change reduces complexity inside the network. Fundamentally, IPv4 succeeded because it was simple and flexible. But unfortunately, the 32-bit address system created a mathematical hard limit. And as the internet expanded, that limit forced the workarounds that you know today, such as CIDR and NAT. V6 solves the problem by expanding the address space to 128 bits and redesigning the key parts of the protocol. So the internet is now transitioning between these two worlds. Understanding how that transition works is the next step. Thanks for watching.